All right. Hi, everyone. Good morning.
Good morning, sir.
Good morning,
Good
sir.
morning,
Morning, sir.
Good morning, everyone. So, couple of things to start with, I guess. इसके पहले this batch was being taught by Vishal sir. Am I correct?
Yes, sir.
Yes, sir.
Okay. Great. So, as an introduction, my name is Gaurav Jasoria, and
Good morning, sir.
and it stands for the short acronym of GJCH. So, I will be taking your physical chemistry lectures going forward. Now, the methodology with which we are going to study is,
Yes, sir.
I'll just quickly put some light to it. So as you can see, I will be sharing the screen, and on the screen, you will have the notes in front of you. I will be taking you through those notes, explaining the concept, and simultaneously expecting you to write handwritten notes. Okay, I will not be sharing the PDF. I will not be sharing the notes with you. I would insist that while we are discussing, while we are in the live lecture, you have your notes, your class notes ka register or notes, notebook with you, and you simultaneously write. Okay. Of course, at times there will be one situation I will ask you to just focus and understand, and then give you time to copy. So those situations are going to be there, and in case, let's say, someone misses out on something, then you can interrupt me in between. Let me know. I will go up or down and let you copy or let you take a screenshot. Okay.
Yes.
Now,
Yes, sir.
in terms of the lecture recording, so I have already broadcasted this over YouTube. Now, if you will, click on that YouTube link that would be available to you, you can save that link for future references, because the lecture will be recorded and kept or stored there. Okay, I will not be sharing alag se any link. So in case someone is missing any lecture, right, they're not attending that lecture, then you can go to the YouTube channel, you can find the lecture there. Maybe it will come the next day. Or if you save the link or ask your friends to save the link for you, then you can access it immediately after the class as well.
Yes, sir.
Okay. Okay. The other thing is the methodology in which we work with the chapter is that I will be teaching you certain concepts in the live lecture, and then based on that I'll be giving you homework. The homework will be primarily from our PACE booklet, as well as there will be some DPP, some extra assignment that I will be sharing.
Yes, sir.
Yes, sir.
I will be putting that over a WhatsApp group. So I will make a WhatsApp group and share the link with you so that you can join that group. And once you are in that group, then us group mein I will be putting the doubts and the extra assignments that you will have.
So we
Okay,
have
sir.
a group already made.
So that is a group. I think it might be a common group. I'll make a dedicated chemistry related group for my track. So you can join that.
Okay, sir.
Yes, sir.
Apart from that, any other questions from your side?
So can you share the thermo DPPs with us?
Thermo DPPs.
Sir.
Not a problem.
Okay. Thank you, sir.
Share all of that.
Yes, sir. Thank you, sir.
Acha. Now, apart from that, I hope आप लोगों का thermodynamics का chapter complete हो चुका है.
Yes, sir.
Yes, sir.
Yes, sir.
Sir.
Okay. And chemical equilibrium, was it started before
No.
EMT or?
No, sir.
No, sir.
No,
No,
sir,
sir.
we have to start it.
We have to start.
Okay. So we have to start. ठीक है. Now, this is a very, very easy chapter. The background behind it's like an extension of thermodynamics. However, even if you have less confidence in thermodynamics, that's not a worry over here. ठीक है, the chapter is very easy. Maybe couple of thermodynamics के concepts are going to come in use, but those are going to be very, very easy concepts.
Yes, sir.
ठीक है, the chapter will not be much long. It will take me around 6 to 7 lectures to complete this chapter. And in terms of the difficulty level, this is, as I said, it's a scoring chapter, it's an easy chapter. The only thing which you need to be very, very cautious about in this chapter is avoiding careless mistakes. Okay, so I will be highlighting the common careless mistakes which students make while we do questions, while we solve problems. Make sure that you highlight those mistakes. Okay, if you have any doubts also coming your way, okay, no matter how silly that doubt is, I would encourage that you ask that doubt, because those doubts are the exact kind of careless mistakes that you are going to make in your exams or your tests. Okay, so better sort
Yes,
them
sir.
or discuss them in the class, highlight them so that you are more aware while giving your exams, while giving your tests.
Yes.
ठीक है, then रहा सवाल आपका MT2 के discussion का. So we'll find a slot sometime, maybe not in this week but next week, and discuss that. And hopefully you would have analyzed your paper. Like, I hope you guys
Yes, sir.
analyzed your major test.
Yes, sir.
Actually, you should analyze all the papers that you give, the topic wise tests as well as major tests, because it's a habit that you need to develop, analyzing your performance and figuring out how you can improve. Right, so you should definitely do that, and then we will take out some time to discuss the paper as well. Acha, now batch ka strength kitna hai? Almost 35 students have joined in.
Yes, sir.
35
35.
35 ही रहता है, ठीक है. So I think then we can start our discussion of the chapter. So let me introduce this topic by first helping you visualize, helping you understand the concept of equilibrium, right? And let me do that using an example. So let's say we have the following setup in front of us. Okay, there is N2O4 gas that we have to begin with, and we take it in a vessel. Okay, it's a vessel of a given volume at a given temperature, and इस vessel के बाजू में there is a manometer that is attached to measure pressure. Now, at time t equal to 0, what we see is that a transparent, like, gas is present inside, so we don't see any color, and there is some reading in the manometer corresponding to some original pressure P0. Now, as time progresses, what we observe is that certain shade of brown starts to appear. This is because NO2 is formed, like N2O4 dissociates into NO2. And NO2, as you remember from chemical bonding, right, is an odd electron species, right?
Yes, sir.
Right, NO2 में ऐसा आपने पढ़ा होगा, एक odd electron रहता है. So because of that odd electron, it has got a paramagnetic behavior as well as color. Okay, so that is why this brown shade is appearing, and the pressure is increasing. You can see that volume and temperature are constant, and यहाँ पर 1 mole से 2 mole बन रहे हैं, या x moles से 2x moles produce हो रहे हैं. तो moles are increasing. Because moles are increasing, the pressure is also increasing, right? And given sufficient time, what we find is that the pressure has become constant. Like, the pressure originally was P0, it increased, and after increasing it became constant, right? And the shade of brown that was there in this vessel, that also became constant. Earlier there was no shade of brown, then there was a lighter shade that appeared, it became darker, and then it became a constant shade of brown. So this situation, जहां पर macroscopic parameters, observable parameters like pressure, color, etc. become constant, okay, become steady, they don't change with time, we say a state of equilibrium has been achieved, right? So यहाँ पर जैसे definition लिखा हुआ है, the state of equilibrium is characterized by macroscopic properties such as pressure, concentration, color, etc. attaining steady or constant values. इसको लिख लो, write this down.
Yes, sir.
Yes, sir.
So do we copy the diagram also?
Yeah.
So I had a question.
बोलो.
So how did it turn into NO2 from N2O4?
Well, it's a reaction that happened.
So like, is it heated more or like how did it turn?
No. So in thermodynamics, आपने second law of thermodynamics में यही सीखा था, that it is the second law that governs whether a reaction would happen or not.
Yes,
Right?
sir.
So this reaction, okay, is happening in the forward direction as per the second law of thermodynamics only, that under the given conditions of temperature, this reaction ka delta G is negative, and as a consequence, the reaction is happening in the forward direction.
Okay, sir. Understood. Thank you.
So, I had a question.
Uh-huh.
So, like pressure is directly proportional to the moles. So that is why the pressure is increasing. That would be safe to use as an argument, right?
Correct.
Okay, sir.
Yes, sir. Done.
ठीक है, सो अभी इसको हम थोड़ा सा और डिटेल में पढ़ लेते हैं. ठीक है, ये तो हम लोगों ने ऐसे ऑब्जर्वेशन पॉइंट ऑफ व्यू से पढ़ा, दैट यू नो द मैक्रोस्कोपिक पैरामीटर्स बिकेम कांस्टेंट. ठीक है, however we can also go in a little bit of more depth when talking about the thermodynamics of it. ठीक है, सो यहाँ पर आप इसका thermodynamics notice करना. Now in last chapter, in previous chapter, okay, you would have noticed that at equilibrium, delta G of a reaction is equal to 0.
Yes, sir.
Yes, sir.
Now यहाँ पर I'm going to put forward an additional piece of understanding for you, that at equilibrium system, okay, the reaction mixture is minimum. ठीक है, कहाँ से आ रहा है ये point? You can simply connect the two statement. Delta G, like if you remember from second law, delta G less than 0 implies,
Spontaneous.
right, the reaction, or you can say the process is spontaneous in forward direction.
Yes, sir.
Yes, sir.
Yes, sir.
Spontaneous in forward direction. I can also write it in this way. ठीक है, डेल्टा जी नेगेटिव का मतलब क्या हो जाएगा? गिब्स फ्री एनर्जी lowers, because delta is final minus initial, na?
Yes.
sir.
Yes, sir.
So I can write this, that the spontaneous direction of a process is the one which lowers Gibbs free energy.
Yes, sir.
Yes, sir.
Yes, sir.
Spontaneous direction of a process, ठीक है, and especially जब हम लोग गिब्स फ्री एनर्जी के कॉन्टेक्स्ट में बात करते हैं तो द कंडीशन इज कांस्टेंट P, T, राइट? ये आपने नोटिस किया होगा. डिड यू नोटिस दिस?
Yes, sir.
हाँ सर.
ठीक है. So when a process is under constant P, T conditions, then we say that the spontaneous direction of the process is towards lower Gibbs free energy. Okay, so the process attains a minima of Gibbs free energy at the equilibrium. Now, let me illustrate this with an example also. पहले आप इतना लिख लो.
Yes, sir.
सर डेल्टा जी इक्वल्स टू 0 उधर क्या लिखा है डेल्टा जी के बाजू में?
Reaction means
Okay.
system. Like यहाँ पे the system is our reaction mixture only.
Okay, so thank you.
Answer.
Yeah, sir. Done.
ठीक है. So now notice करना इसको further explain करने के लिए, like if I like try to ask you a question. Okay, let me put forward a question in the in the context of an example. Say we are trying to study an equilibrium between these species, right? A very common example that you have come across.
It was.
Okay. Now, if we start with only N2 and H2, then I think very intuitive answer comes to you. Then reaction goes forward
Yes, sir.
Yes, sir.
Yes, sir.
and attains equilibrium. Okay. How much forward? Well, we don't know that. We need to work on that calculations. We'll talk about it later. But we are sure that if we are just starting with N2 and H2, okay, it will go in forward direction and attain equilibrium. Okay. If we start with only ammonia, what will happen?
The action goes backward.
Backwards until equilibrium is attained.
Right. So that was also an intuitive understanding.
Yes, sir.
If we
Yes.
start with only ammonia, right, then the reaction goes backward and attains equilibrium, right? How much backward? Well, that depends. That depends on data. That depends on something which we are going to do the calculation for. Okay.
Yes, sir.
Acha, what about if I give you some mixture? Of reactants and products. What is it that is going to happen? If we start with some mix of N2, H2 and NH3, where would the reaction go?
Sir, it would depend upon the concentration of
Yes, sir.
each element.
So
Each
depending on the reactants and products, whichever is less in concentration as compared to the other, the reaction
And
will
then
go towards that side
depending on
until
that,
equilibrium is attained.
नहीं आपका आवाज बहुत डाउन था, लाइक समझ में नहीं आया, कुछ कहा आपने, you made some statement.
हाँ, so basically depending upon the concentration or the rate, not rate of process, मतलब जितना भी process होना चाहिए, जो भी कम होगा उसके तरफ हो जाएगा process until equilibrium is attained.
ठीक है, तो आपने रेट के पर्सपेक्टिव से बात करा. चलो अभी मैंने रेट का कॉन्सेप्ट तो सिखाया नहीं है, बट ठीक है, फेयर इनफ कॉन्सेप्ट, बात करेंगे उसके बारे में भी. From a thermodynamics perspective, okay, what we can say is that if you start with some mixture of N2, H2 and ammonia, the reaction goes towards minima of Gibbs free energy to attain equilibrium. Okay, this is the thermodynamic perspective. So इसको मैं ग्राफ से भी आपको एक्सप्लेन करता हूँ. ठीक है, नोटिस करना, यहाँ पर एक ग्राफ आपके सामने है. On the y-axis, what is it that we are plotting?
Gibbs free energy.
Oh, system.
Free energy of the system. On the x-axis, we are plotting what we call as reaction coordinate. Reaction coordinate or reaction progress. Okay, so on the left hand side, reaction progress is 0%. That means only reactants are there. Okay, N2 and H2. On right hand side, you have 100% reaction progress. मतलब only ammonia is there. Okay. Now,
Yes, sir.
यहाँ पर notice करना, the if let's say there is only reactants and उनके साथ associated कुछ Gibbs free energy था, right? तो natural direction, spontaneous direction किधर रहेगा?
It will
Towards
head downwards.
Towards right.
lowering of Gibbs free energy.
Yes, sir.
Yes, sir.
Yes, sir.
ठीक है. If you had products, say only products, and उनका कुछ Gibbs free energy था, ठीक है, कुछ भी हो सकता है, कम ज्यादा, I don't care. But अगर say products ही थे, तो what would have been the natural direction?
Tending to lower Gibbs free energy.
Tending to
Lower.
lower Gibbs free energy, right? That is backward.
Yes, sir.
Yes,
Yes,
sir.
sir.
There exists a point somewhere, ठीक है, we don't know where, that depends on data. It could be at 10%, 20%, it could be 99.9999%, but there would be some position, ठीक है. Let me randomly mark a place जहां पर equilibrium होगा, ठीक है. This would correspond to the minima, ठीक है, not zero, minima of Gibbs free energy, right? So the Gibbs free energy would be, say, something in the following manner. ठीक है, let me make a better plot of it. ठीक है, it could be, in fact, ऐसा भी हो सकता है. Let me make a plot in this manner. यहाँ पे minimum बना देता हूँ. right? So this is the point where you are seeing the equilibrium is.
Yes, sir.
Yes, sir.
ठीक है, अगर मान लो हम लोग कोई ऐसे कॉम्पोजिशन पर है which is say towards the left hand side. So here
Yes, sir.
towards the left hand side you can see the spontaneous direction is what?
Down.
Spontaneous direction, ठीक है. यहाँ पे अगर आप स्लोप देखोगे, स्लोप इस ग्राफ का कैसा है? नेगेटिव.
Negative.
Negative.
तो यहाँ पे spontaneous direction is फॉरवर्ड.
Yes, sir.
Yes, sir.
Forward, yes, sir.
अच्छा, यहाँ पे आप स्लोप देखोगे, स्लोप कैसा है?
Positive.
राइट, पॉजिटिव है स्लोप, राइट. तो
Yes, sir.
स्पॉन्टेनियस डायरेक्शन क्या है यहाँ पे?
Backward.
Backward.
बैकवर्ड. एंड एट मिनिमा स्लोप क्या रहेगा?
0.
0.
राइट. तो डेल्टा जी वहां पर आपका
0 हो जाएगा.
डेल्टा जी इज 0 एट दिस मिनिमा. ठीक है, एट इक्विलिब्रियम. ना तो फॉरवर्ड जाएगा ना बैकवर्ड जाएगा, लाइक इट विल हैव इक्वल एंड ऑपोजिट टेंडेंसी. ये समझ में आया फ्रॉम अ थर्मोडायनामिक्स पर्सपेक्टिव?
Yes,
Yes,
sir.
sir.
Yes, sir.
ठीक है. अब ये इक्विलिब्रियम कहाँ पे हो सकता है? वो तो रिएक्शन टू रिएक्शन वेरी करता है. ठीक है, किसी का फॉर एग्जांपल ये मिनिमा मान लो यहाँ पे भी हो सकता है 0% पे, 0.001% पे, या 1% पे. ठीक है, कि हार्डली फॉरवर्ड गया और इक्विलिब्रियम आ गया. कुछ ऐसे रिएक्शंस भी हो सकते हैं जिनका मिनिमा यहाँ पे लाया करता हो ऑलमोस्ट 99% पे. ठीक है. सो दैट इज समथिंग व्हिच डिपेंड्स ऑन द सिचुएशन, डिपेंड्स ऑन द रिएक्शन.
Yes, sir.
Yes, sir.
लिखो इसको.
Done, sir.
अच्छा, लिखा सबने?
Yes, sir.
Yes, sir.
ओके. तो यहाँ पे आप एज अ नोट लिख सकते हो that the state of equilibrium can be achieved from any direction. That is, if we start with only reactants or only products or any combination of reactants and products, we will eventually achieve the state of equilibrium.
Yes, sir. Done, sir.
अच्छा,
So
now
1 minute. Yes, done.
now I have used the term forward backward reactant product, so I want to like eliminate any confusion over it by putting across this convention. ठीक है, जैसे for example you have a reaction, ठीक है, the example that we discussed ऊपर, N2 gas plus 3 H2 gas giving say 2 NH3 gas, right? Now in a question maybe N2 or H2 are given to you, ठीक है,
Yes, sir.
or maybe say ammonia is given to you, ठीक है, no N2 no H2, ammonia is given to you. Now that should not change your language. That should not mean कि अरे अमोनिया दिया हुआ है और अमोनिया कंज्यूम होगा और N2H2 प्रोड्यूस होगा, तो फिर अमोनिया को रिएक्टेंट बोल देते हैं और N2H2 को प्रोडक्ट बोल देते हैं. ऐसा मत करना. What you need to understand is a very, very simple convention that you need to follow. Whatever is the written form, okay, the written form is crucial. Whatever is the written form of the reaction in front of you, तो उसमें whatever is on the left hand side you will call that reactant, whatever is on the right hand side you will call it product. Okay, doesn't matter which species is written where. Whatever left is reactant, whatever right is product. Going from left to right will be called as forward, going from right to left will be called as backward. ठीक है?
Yes, sir.
Yes, sir.
इसको भी लिख लो. इसमें से कुछ कुछ नाम मुझे ऐसा लग रहा है पहले फ्लैगशिप बैच में भी थे क्या? विरोक, तुम पहले फ्लैगशिप में थे?
Sir, like the last year I was in the flagship 2 batch for a few lectures of atomic structure.
अच्छा अच्छा, हाँ मतलब.
And I attended the KPY lecture.
और भी कुछ कुछ क्या जो अलग से नाम रहते हैं उनका फिर भी ध्यान रह जाता है, बाकी तो कॉमन कॉमन नाम है. ठीक है, लिखा सबने?
Yes, sir.
Yes, sir.
Okay. Now, notice करना, there is another clarification which I would want to put forward in the beginning itself, which is the concept of reversible and irreversible chemical reaction. ठीक है, आप लोगों ने ये टर्म्स जूनियर क्लासेस में सीखे होंगे.
Yes, sir.
Right. What do you mean by reversible reaction?
So actions that take place in
Infinitely small steps.
No, like no other definition for a reaction is that we proceed in any direction, forward and backward.
So जो reversible and irreversible का, ठीक है, मीनिंग आपको थर्मोडायनेमिक्स में सिखाया गया था. That was the correct or true meaning of reversible and irreversible process. However, the words reversible reaction and irreversible reaction, okay, this is something which is not at all related to what you had studied in thermodynamics. Okay, these are something which are defined more out of convenience, जो कि आपने जूनियर क्लासेस में पढ़ा था. ठीक है, क्या पढ़ा था आप लोगों ने जूनियर क्लासेस में?
reversible reaction takes place.
Action. can occur in both forward as well as backward manner.
Yes, sir.
Yes, sir.
Yes, sir.
Whereas
Yes.
an irreversible reaction is something which will be happening primarily in the forward direction only, right? So that was something which you studied in your junior classes, and was a definition which was a good definition from that class perspective, because of the convenience it provided. However, यहाँ पर notice करना, एक clarity जो मैं आपको दूंगा, ध्यान से सुनना और समझना, that all reactions in a closed system are going to attain equilibrium. ठीक है, अभी एक बार पहले सुन लेना. I'll give you time to copy later. First focus on the screen itself. Reactions in a closed system are going to attain equilibrium. Now, some reactions, they proceed almost 100% forward to attain equilibrium. So for example, HCl plus NaOH, if you will mix, we represent this with a single forward arrow saying it's an irreversible reaction. You know?
Yes.
Because it is almost 100% in the forward direction, like 99.9999999999%.
Yes, sir.
Okay, that is where it achieves its equilibrium, almost going 100% in forward direction. Okay, but this representation is, as I said, from the point of view of convenience, right? We call this as irreversible reaction because, say, in a chapter like mole concept, assuming this to be in the 100% forward reaction was easy for us to calculate kitne moles consume honge, kitne moles produce honge. But आप notice करना, the same reaction, ठीक है, the exact same reaction, H plus plus OH minus giving H2O, right? If you would want to study that in depth, ठीक है, if you want to study the same reaction in depth, right, and we will be doing that in an upcoming chapter, तो वहां पर आप notice करना, the same reaction will be represented in the double-headed arrow manner. I will be doing H plus plus OH minus, and I will be doing a double-headed arrow giving H2. Because उस chapter में we would be interested in knowing कि अगर ये 99.9999% था तो कितने 9 लगाऊं मैं, ठीक है? That is the depth we would want to explore. Mole concept में क्या था? Mole concept में we did not bother. Like for example, mole concept में question था कि 1 mole HCl and 2 mole NaOH, let's say, are mixed, and I ask you how much NaCl will get formed. What will be your answer?
1 mole.
1.
1 mole, right?
Yes.
Yes,
ये
sir.
लिमिटिंग रिएजेंट होगा. अब लेकिन अगर मुझे इसी रिएक्शन को डेप्थ में स्टडी करना होगा, ठीक है, इन अनदर चैप्टर आयनिक इक्विलिब्रियम में, तो उसमें आप नोटिस करना, उसमें आई वुड बी इंटरेस्टेड, ठीक है, इन नोइंग इवन द डिटेल्स ऑफ दिस ऑलमोस्ट 100%. लाइक ये 100 है तो 100 का कितना 99.999999 कहां तक है, ठीक है? दैट इज समथिंग विच विल बी एक्सप्लोरिंग. तो वहां पर हम लोग क्या करेंगे, इसको एक इक्विलिब्रियम की तरह ट्रीट कर लेंगे, ठीक है? तो ये जो टर्मिनोलॉजी थी, रिवर्सिबल and irreversible chemical reaction, this is, as I said, more out of convenience. The reality is all reactions are reversible only, like all reactions attain equilibrium in a closed system. Certain reactions which are like almost 100% forward, right, we generally represent them using single arrows.
Yes.
तो ये क्लैरिफिकेशन समझ में आया?
Yes, sir.
हाँ
Yes,
सर.
ठीक है, लिख लो इसको.
So I had a question.
हाँ,
So what about an open system? Like the reaction तो बताया वो attain.
ओपन सिस्टम में इक्विलिब्रियम अटेन होना मुश्किल रहता है, ठीक है, बिकॉज द स्पीशीज कैन एस्केप.
Into the surrounding.
Especially let's say if there are gaseous species involved, then open system is difficult to study equilibrium.
Yes. Done, sir.
ठीक है. All right. So let's understand equilibrium from another perspective. I think थोड़ी देर पहले कौन बोल रहा था? Like who had spoken about the rate perspective?
So me.
Soham.
Yes, sir.
ठीक है. हाँ, तो Soham talked about the concept of equilibrium from a rate perspective. Rate perspective मतलब कितना अमाउंट कितने टाइम में कंज्यूम हो रहा है या कितने अमाउंट कितने टाइम में प्रोड्यूस हो रहा है, राइट? सो दैट इज रेट. We call it kinetics. So that is also a perspective through which we can understand the concept of equilibrium, right? So this is in the following manner. Okay, let's say we take the original example of N2O4 and NO2, right? And we started by taking only N2O4, right? So what will happen? Initially, the reaction proceeds in forward direction. Why? Because we started with N2O4 only, right? Initially, the forward reaction is happening much more as compared to the backward reaction, because there is hardly any NO2 that is there. Okay, the moment NO2 gets formed, the backward reaction also starts to happen. But because the quantity of NO2 is very, very small, the rate at which the reaction proceeds in backward manner is very less. Predominantly, it is forward only. So यहाँ पे I have used a longish arrow to represent greater forward rate and a small arrow to represent the small backward rate. But as time proceeds, what will happen? ठीक है, अभी पहले यहाँ पे स्क्रीन पे देखना. I'll give you time to write. What will happen now? After some time, the amount of reactants is going to go down. ठीक है, ये जो N2O4 है ये कंज्यूम होता जाएगा. तो as a consequence, जो forward rate है, that is going to decrease because the amount of reactants has decreased. And what about the backward direction? ठीक है, the product का amount has increased with time. As a consequence, the backward reaction का rate will increase. Right? There will come a time जहाँ पर rate forward and rate backward will start to approach each other. ठीक है, and of course, eventually there will come a situation जहाँ पर both will become equal and opposite. The rate of forward reaction will be equal to the rate of backward reaction, right? And the reactions won't stop. Right? The rates will not be zero, will be finite values, but in equal and opposite manner. And we say that is the condition of equilibrium. That is where the concentrations will become constant. Because, for example, N2O4 is getting consumed, say in 1 second it is getting consumed 2 moles. At the same time, in 1 second it is getting produced also 2 moles. Right? So the overall concentration or the amount becomes constant. Okay? The reactions keep on happening. They don't stop. Okay? The equilibrium is I think my internet got disconnected in between.
Yes, sir.
Yes, sir.
Now,
Yeah, so we
हाँ,
can
yeah.
hear you.
Yes, sir.
कहाँ तक आवाज आ पा रहा था? यहाँ तक का पार्ट
So
सुन
last
पाए थे आप?
statement बचा था.
And last statement बता दो.
ये पार्ट
Yes, sir.
हाँ
Done.
सर.
Yes, sir, ये हो गया.
ये हो गया सर.
Reaction does not stop.
ठीक है, तो पहले इतना कॉपी कर लो, फिर मैं वो ग्राफ वाला भी वापस से समझा दूंगा.
Yes, sir.
इतना कॉपी कर लो फ्रॉम द पर्सपेक्टिव ऑफ काइनेटिक्स.
Sir, so I had a question.
हाँ, बोलो बोलो.
Sir, so like the concentration would then become constant at state of equilibrium for
Yes.
So, but then the reactions have proceed in both directions. So, shouldn't the concentrations fluctuate?
But they are proceeding in equal and opposite manner, na? So in 1 microsecond, say some molecules got formed. In the same microsecond, some molecules will, the same amount of molecules will get consumed also.
Okay, sir.
So the concentration is steady. It is constant.
So it'll be equilibrium only for that microsecond, right?
No. So this happens every microsecond. तो जैसे ये अभी मैंने ग्राफ में आपको बताया, तो ग्राफ में बिफोर इक्विलिब्रियम इज अचीव्ड द रेट्स आर डिफरेंट. ठीक है, सो नेट रेट इज से फॉरवर्ड और बैकवर्ड, बट पोस्ट इक्विलिब्रियम व्हेन बोथ द रेट्स हैव बिकम इक्वल, राइट, they are happening in equal and opposite manner, so concentrations are going to be unchanged.
So once
They are going to
equilibrium
become
is
constant.
achieved,
Achieved.
it just stays there.
That's
Okay.
what the concept of equilibrium is, no?
Yeah, sir.
So had the graph been had equilibrium been static in nature, so the end of that graph would have just gone down at that export rate.
हाँ, मतलब the rates should have been in zero.
Yes, sir.
But that is not the case. The rates aren't zero. They are something finite, but in equal and opposite manner.
Yes, sir.
ठीक है, इतना लिखा ना सबने?
So 1 minute.
हाँ सर. Yes sir. Thanks.
ये एट इक्विलिब्रियम वाला भी लिख लिया था बुलेट पॉइंट?
Yes sir. Yes sir, लिखिए.
Yes, sir.
ठीक है, तो उसके बाद आप ये ग्राफ के पर्सपेक्टिव से भी समझ सकते हो that a graph of rate versus time talks about that initially the rates are different. ठीक है, in the above example the forward rate is some higher value, the backward rate is 0, but as time progresses the forward rate decreases. ठीक है, and the backward rate increases, and eventually they are going to become equal, and that is the point where we say the equilibrium has been achieved. Before that we say it's a non-steady state, the concentrations keep on changing, but at equilibrium or the concentrations will become constant.
Done sir.
Answer.
So after understanding this background, let's talk about the numerical part of equilibrium. Okay, what do I mean by numerical part?
So determining by how much the reaction moves forward or backward.
Correct. Right. So that is the next obvious question that is coming to our mind, that okay, some reactions proceed almost 100% forward. Now, if they proceed 99.999 or 99 point quadruple nine, doesn't matter to me. I am fine writing them 100%. And that is what we did in mole concept chapter, right?
Yes, sir.
Yes sir.
But now we are interested in those examples where we understand that an equilibrium is achieved. So a reaction might not go 100%, may go 70%, may go 60%, 20%, right? So how can we get that calculation right? That is what we are looking at. Now, before I give an answer to that, okay, or you can say the answer to that question lies in two ways. One is experimental and the other is theoretical. Experimental is that you do the experiment, okay, and get the data. For example, मान लो ये जो हमने N2O4 वाला एग्जाम्पल लिया था, राइट? इसमें you remember that we were measuring pressure?
Yes, sir.
Yes, sir.
Right, so यहाँ पे हमने मैनोमीटर लगा रखा था. Let's say initial pressure was and we started with the N2O4 only. ठीक है, we start with N2O4 only and initial pressure was 1 atm. And what we find is that equilibrium जब आ जाता है, like eventually after a long time, the total pressure, ठीक है, of the reaction mixture was say 1.5 atm. ठीक है. Now based on this experimental information, can you tell me what would be the extent of reaction? Like how much would it be going forward?
Sir, would be going forward because pressure is increased.
Sorry?
So the reaction will be headed forward because the pressure is increased. So
हाँ, so I'm asking how much forward? 10%, 20%, 50%, 90%?
So around 50 to 75%.
66%.
तुक्का क्यों मार रहे हैं? कैलकुलेशन करने के लिए बोल रहा हूँ, डेटा दिया है मैंने. मतलब तो लाइक गेस वर्क में लग गए कि हाँ सर 70% अच्छा लग रहा है सर बोलने में. हम लोग मैथ कर सकते हैं ना यहाँ पे. देखो ये स्टार्टिंग में 1 था, ये 0 था, राइट?
Yes, sir.
अब इसमें से मान लो x मोल्स रिएक्ट हुए होंगे तो इधर 2x मोल्स प्रोड्यूस हुए होंगे,
yes, sir.
हाँ
Yes,
sir.
sir.
है ना, राइट?
Stoichiometry we can apply that.
तो फिर इक्विलिब्रियम पे इसके 1 - x मोल्स होंगे और इसके 2x मोल्स होंगे.
Yes, sir.
Yes, sir.
Yes, sir.
अच्छा, अभी v, d कांस्टेंट है तो इसका मतलब मोल्स आर प्रोपोर्शनल टू प्रेशर, है
Yes,
ना?
sir.
तो इनिशियल टोटल मोल्स अपॉन इनिशियल टोटल प्रेशर विल बी इक्वल टू इक्विलिब्रियम पे टोटल मोल्स अपॉन इक्विलिब्रियम पे टोटल प्रेशर.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
इनिशियल मोल्स 1 थे, है ना,
हाँ
और
sir.
इनिशियल प्रेशर कितना था? 1 atm, जैसा यहाँ पे
Yes.
बताया मैंने, राइट? ये 1 atm था ना प्रेशर, मैंने बोला ये
हाँ,
दिया
sir.
डेटा आपको. और इक्विलिब्रियम पे मैंने क्या बोला? इक्विलिब्रियम में प्रेशर कितना हो गया? 1.5 atm,
1.5.
है ना? और मोल्स कितने हो गए? मोल्स इफ यू ऐड तो ये कितने मोल्स दिख रहे हैं? 1 - x plus 2x,
Yes, sir.
that is 1 + x.
Yes.
तो इसमें x कितना आ गया? 0.5.
Yes, sir.
हाँ sir.
x 0.5 आ गया तो मतलब कितना हो रहा है रिएक्शन? 50% हो रहा है.
50%.
हाँ sir.
ठीक है. सो दिस कैलकुलेटिंग ऑफ इक्विलिब्रियम, ठीक है, कितना जाएगा फॉरवर्ड या कितना बैकवर्ड, ये हम लोग कैसे कर सकते हैं? इट कैन बी बेस्ड अपॉन 2 data points, right? One was experimental, right, that you analyze the reaction under given conditions, and the other is theoretical. ठीक है, theoretical data. Now, of course, as you know that we are giving a subjective paper, we are not doing a lot of experiments with us right now. So what is it that our chapter is going to be more focused on? What is it that we are going to do?
Theoretical data.
We are going to rely on theoretical data. ठीक है, what theoretical data? So that theoretical data is what we call as equilibrium constant. तो एक reaction का equilibrium constant, ठीक है, will be that theoretical data that will help you calculate the equilibrium and its information. Now, ये आता कहाँ से है? Theoretical data, that is something which is not under our syllabus. ठीक है, that is something we will use but not get into the derivation of. ठीक है, ये बेसिकली थर्मोडायनेमिक्स से आता है. जो रिएक्शन का थर्मोडायनेमिक्स होता है ना, लाइक उसका रिएक्शन का डेल्टा एच, डेल्टा एस, डेल्टा जी, ये सब कैलकुलेशन से, ठीक है, ये इक्विलिब्रियम कांस्टेंट का वैल्यू आता है. नाउ वी आर नॉट गोइंग टू गेट इनटू द डेरिवेशन ऑफ इट, दैट कैसे थर्मोडायनेमिक डेटा से ये आता है. फॉर अस इट इज गोइंग टू बी मोर लाइक कि we are getting a direct access to this data. ठीक है, we will get directly information about this equilibrium constant, this capital K. Once we have that, we will now see how to use it and solve it. ठीक है, background समझ में आया?
Yes, sir.
Yes, sir.
Okay, now how to use it is what is this law of chemical equilibrium about. ठीक है, आप पहले इतना लिख लो, फिर मैं आपको फर्दर एक्सप्लेन करता हूँ. ठीक है,
Sir, can you
Write
scroll
this-
up a little bit?
अब कहाँ गया? अब तो पहले लिख लिया
बस
ना
ये
सब.
ग्राफ कॉपी करना था.
अच्छा, स्क्रीनशॉट ले लो.
डन सर.
ठीक है, तो अभी आप पहले इतना लिख लो, फिर मैं आपको एक्सप्लेन करूंगा.
Done.
Alright, लिखा सबने?
So 1 minute.
1 minute.
Okay, so what is it saying? यहाँ पे notice करना that chemical reactions have a characteristic constant for the state of equilibrium, which we call as equilibrium constant, capital K. Now this is, as I said, calculated based on thermodynamics, right? For a given reaction at a given temperature, based on thermodynamic data. Okay. You can say this equilibrium constant is calculated, and as per the law of chemical equilibrium, okay, this equilibrium constant is equal to activity of products raised to the power of their coefficient divided by activity of reactants raised to the power of their coefficients. What do I mean by activity? Now, this itself is also a thermodynamic term. Okay, like in order to describe reaction species and reaction species ka amounts, right? What are the terms that you have come across? Mass, moles, concentration, partial pressure, like many terms you have come across.
Yes, sir.
So, वैसे ही there is this another term called as activity. We also relate it to something called as chemical potential. Okay. So this is a thermodynamic term which represents how participative a species is in a given reaction as compared to its standard state. Now, you remember standard state in thermodynamics आप लोगों ने define करा होगा.
Yes.
अगर कोई gaseous species है तो उसका standard state was ideal gas at 1 bar partial pressure under any given temperature. अगर कोई dissolved species है तो उसका standard state क्या होता था? कोई dissolved species है, aqueous species है, तो उसका standard state was 1 molar concentration under 1 bar pressure at any given temperature.
Yes, sir.
Right? कोई solid या liquid species था तो उसके लिए standard state क्या होता था? Pure solid, pure crystalline solid या pure liquid under 1 bar pressure at any given state, at any given temperature. Right? If temperature was not mentioned, we took it to be 298 Kelvin.
Sir.
Right? So what it is saying is that activity of a species describes how participative a species is in a given reaction as compared to its standard state. ठीक है, तो जैसे मान लो ये रिएक्शन है N2 gas plus 3H2 gas giving 2NH3 gas. Now, what would be the standard state? N2 is at 1 bar partial pressure, H2 is at 1 bar partial pressure, ammonia is at 1 bar partial pressure. This will be the standard state. Okay. Now, as compared to this state, okay, you can have a non-standard state. Non-standard state कैसा हो जाएगा? Say this is P1 bar, this is P2 bar, and this is P3 bar. Okay, P1, P2, P3 are some random values. Now, in this state, how a reaction species is participating as compared to its standard state is what is described by the activity. Okay? Now,
Yes, sir.
the thing is, activity itself is a term which we define and calculate in thermodynamics, but not in our syllabus. Okay, maybe if you will study higher thermodynamics, if you pursue say chemical engineering or mechanical engineering, you might come across the detailed thermodynamic aspects of activity and its calculation. But as per our syllabus, the accurate calculation of activity is not there. Okay, what we do is take certain approximations, and these are like universally accepted approximations. ऐसा नहीं है कि सिर्फ JEE के लिए हम लोग ले रहे हैं. Even the standard textbooks that you come across have these approximations. What are these approximations? For gases, we replace activity by their partial pressure. For dissolved species, we replace their activity by their molar concentrations. And for solids and liquids, the activity we say doesn't change much as compared to their standard state, right? So we take the value as 1, like we assign it a constant value of 1 and move on. Okay, these approximations are going to work fairly well in the context of low pressure and low concentration situations. However, हमारे syllabus के हिसाब से we are always going to take these approximations for activity. We are not going to get into any calculations related to activity.
Okay, sir.
ठीक है, तो इसको आप लिख लो. Rub this.
Samsung.
One.
Done, sir.
Now,
सर
हाँ बोलो.
सर हम लोग जीनथ 1 के एक चैप्टर पीछे चल रहे हैं.
Zenith 1 के हाँ, Zenith 1 में chemical equilibrium complete हो गया.
हाँ.
We just started the ionic equilibrium there.
Yes, sir.
उनका मैंने MT के पहले ही करा दिया था chemical equilibrium. Like I had time.
हाँ sir.
Like I'll not waste that time. Now, having understood this, notice करना यहाँ पर there is like an important note that technically speaking, एक्टिविटी का डेफिनेशन आपने देखा तो इट्स अ रेशियो, like it is participation with respect to standard state.
Yes, sir.
Yes, sir.
Okay, so technically speaking, activity has no units, and if activity has no units, then K also does not have any unit.
Yes, sir.
Yes, sir.
Okay, so that is the technically correct statement. Activity has no units and K is dimensionless. However, because we have taken this approximation, okay, replacing activity with partial pressure or molar concentration, depending upon what kind of species, we then, because of that, report K with appropriate units. जैसा आप ये example notice करोगे, say this is an example of zinc solid plus 2HCl giving ZnCl2 plus H2 gas, right? So इसका मैं equilibrium constant का expression कैसे लिखूंगा? Products का activity raised to the power of their coefficient divided by reactants का activity raised to the power of their coefficient. Now product में ZnCl2 is aqueous, तो उसका activity are replaced by its molar concentration raised to the power of its coefficient. H2 is gas, so I replace its activity by its partial pressure raised to the power of its coefficient, right? Zn is solid. Solid के लिए मैंने क्या बोला? I take the activity as 1 for solids and liquids.
Yes.
And HCl is again an aqueous species, so I replace the activity by its molar concentration and raise it to its coefficient. Okay, raise it to the power of its coefficient. तो इससे अब मेरा K का यूनिट आ जाएगा. कैसे? This ZnCl2 will be in mole per liter या molar.
Yes, sir.
This partial pressure of H2 will be in bar and the concentration of HCl will again be in molar, right? तो उसका स्क्वायर करेंगे तो मोलर स्क्वायर आ जाएगा. तो it will be bar upon molar या फिर you can say atm upon mole per liter. ठीक है, depending upon which units you choose to work with. ठीक है?
Yes, sir.
Yes, sir.
So if I ask you to write down the expression of equilibrium constant for this equation, can you do that?
Yes, sir.
Yes, sir.
Try करो.
So 1 by ATM square.
Correct. Right. अगले रिएक्शन का right bro. राइट? एक्सप्रेशन लिखने में आ रहा है?
Yes, sir.
Yes.
Yes, sir.
ओके. मोल्स पर लीटर या मोलर. ठीक है. नाउ let's understand a bit more about this equilibrium constant, capital K, of a reaction. So a very, very important understanding that you must have. See, from the above expressions that we have seen for, different examples, it might look like that the equilibrium constant depends on pressure of species, their concentration, their moles, right? ऐसा लग रहा होगा? Like if you look at this,
Yes, sir.
Yes, sir.
but it is
Dash
the
is the unit.
but it is the opposite way. It is the other way around. K is actually the cause, and these partial pressures, concentration, moles, these are the effect. For example, say for a reaction like this, okay, at a given temperature, the K value is thermodynamically calculated. Okay, so for the reaction, say at 200 or 300 Kelvin, this is the value of K. ठीक है, कहां से आ रहा है ये? This is thermodynamically calculated, and it does not matter, okay, what quantity or partial pressure of N2, H2, ammonia you start the reaction with. Okay, it is not going to matter. This is the reaction, this is the temperature, and for this reaction at this temperature, this is the thermodynamically calculated value of K. Now, whatever quantity of N2, H2, ammonia you start the reaction with, the reaction is going to proceed in forward or backward manner such that the partial pressures or the moles, they change, they adjust and satisfy this expression of K.
Yes.
Yes, sir.
समझ में आया?
Yes, sir.
ठीक है, तो इसको लिखो, फैक्टर्स अफेक्टिंग इक्विलिब्रियम कांस्टेंट, एंड उसमें ये सबसे इंपॉर्टेंट चीज हाईलाइट करो, which is like a common misconception that students have कि अरे सर वो एक्सप्रेशन से तो ऐसा दिख रहा है कि कंसंट्रेशन डबल कर देंगे तो लाइक रेट ये इक्विलिब्रियम कांस्टेंट भी डबल हो जाएगा, या प्रेशर हाफ कर देंगे तो इक्विलिब्रियम कांस्टेंट हाफ हो जाएगा. ऐसा कुछ नहीं होता है. दिस इज द कॉज, दीज आर द इफेक्ट्स, not the other way around.
Done, sir.
मारे बड़ा फास्ट लिखे तो तू हैंडराइटिंग बहुत फास्ट है तुम्हारी बाकी लोगों ने भी लिखा क्या
No, sir.
So 1 minute.
sir.
ऐसे ज्यादा तो नहीं लिखा दिया आज फर्स्ट डे
No, sir.
ऐसा नहीं है तुम लाइक ऑनेस्टली बता सकते हो नो प्रेशर
नहीं सर, आई गॉट यूज्ड टू दिस। मैं थर्मो आपके रिकॉर्डिंग से कर रहा हूँ तो।
अच्छा
हाँ सर।
बट तुम करंट टॉपिक्स को डीप्रायोरिटाइज मत करना
हाँ हाँ सर। सर वो मैं अपने टाइम पे कर रहा हूँ जब भी टाइम मिलता है।
ठीक है लिखा आपने
Yes.
यस सर।
Yes, sir.
okay so now let's look at the factors on which k depends ठीक है the actual factors तो उसमें the only true factor on which k would depend for a reaction is temperature that is the only fundamental factor how it will depend वो हम थोड़ा टाइम बाद देखेंगे when I will be discussing the thermodynamics part also ठीक है that temperature बढ़ाने से k बढ़ेगा या कम होगा all of that we will discuss right now it is important to just highlight that it is temperature ठीक है on which k would depend then there is or there are two more factors on which k depends but it is not you can say true factor it is more like mathematical adjustment so one such factor is stoichiometry why is this a factor because of the definition of law of equilibrium kaisa tha definition that equilibrium constant for a reaction is products raised to the power of their coefficient upon reactants raised to the power of their coefficients
Yes, sir.
so if I change the coefficients the k value will also change or will you can say have to be adjusted
Yes, sir.
यस सर।
right? so for example यहाँ पे आप नोटिस करना अगर मैंने रिएक्शन ऐसे लिखा हुआ है a plus 2b is giving 3c so this is the expression of equilibrium constant
Yes, sir.
right
Yes, sir.
and say the value is 100 ठीक है I've just taken a random value say 100 now if I rewrite the equation in the following manner ठीक है मैंने क्या करा 2 से मल्टीप्लाई कर दिया थ्रू आउट 2a plus 4b is giving 6c 2 से थ्रू आउट मल्टीप्लाई कर दिया तो उससे क्या होगा जो मेरा डेफिनेशन है इक्विलिब्रियम कांस्टेंट का दैट विल बी प्रोडक्ट raised to the power of its coefficient upon reactants raised to the power of its coefficient so it
Yes, sir.
becomes square of the original value
Yes, sir.
Yes, sir.
so it is more like a mathematical adjustment that if I change the stoichiometry I should accordingly change the value of k also ठीक है इतना लिखो लिखा है इतना?
So on.
Done, sir.
अच्छा
अगर यहाँ पर नोटिस करना, मैं रिएक्शन को फ्लिप कर देता हूँ, right? It is as good as multiplying the reaction by -1, right? So whatever
Yes,
was
sir.
on left hand side went to right hand side, and whatever was on right hand side came to left hand side. So if I multiply by 1, then the new k will be raised to the power of -1.
Yes, sir.
Yes, sir.
yes sir
रेसिप्रोकल हो जाएगा, ठीक है? So whenever I multiply a reaction by a certain factor, तो मेरा जो नया k होगा, it will be the original k raised to the power of that factor. समझ में आया?
Yes, sir.
Yes, sir.
हाँ सर
अच्छा, नेक्स्ट नोटिस करना दैट इज मोर लाइक जैसे थर्मोकेमिस्ट्री में मैनिपुलेशन होते थे, ठीक है? वैसे आप नोटिस करना, if I add two reactions, then their equilibrium constants will get multiplied. तो फॉर एग्जाम्पल मान लो एक रिएक्शन है A goes to B, and इसका equilibrium constant is K1, which is concentration of B upon concentration of A. And then there is another reaction B goes to C, and उसका equilibrium constant is K2, which will be C by B. Now if I add these two reactions, ठीक है, तो ये B cancel out हो जाएगा, and I'll get
Yes,
this
sir.
as the reaction A goes to C.
yes sir
Yes, sir.
Yes.
तो इसका equilibrium constant रहेगा K3, which will be C upon A. So you can notice that this K3 will be equal to K1 multiplied by K2. ठीक है? So if I add reactions, then the equilibrium constants get multiplied.
yes sir
लिख लो इसको भी.
Done, sir.
Right? So let's say if I ask you this question. So can you give an answer?
yes sir
Try करो. ये मैनिपुलेशंस आपने थर्मोकेमिस्ट्री में करने सीखे थे ना?
Hess's law.
राइट? कैसे होते थे मैनिपुलेशंस?
Reaction को flip कर देना.
So right, if I ask you, how can I write the third equation in terms of the first and the second?
So you can multiply the first by 2 and flip it.
No, but I don't want the coefficient of A to be 2 ना. जैसे
हाँ,
थर्ड में मुझे A चाहिए, ठीक है? अब फर्स्ट और सेकंड में ए कहाँ पर है?
First one.
फर्स्ट रिएक्शन में. I want it on the left hand side. Is it on the left hand side?
No, sir.
तो K2 का रूट लेना पड़ेगा.
Yes, and flip it.
हाँ,
One
I
by
want
root
the
K.
coefficient of A to be 1. The coefficient of A is 1 only. तो मैं as it is first reaction को use कर लेता हूँ. ठीक है. Then what is it that I want? I want C on the right hand side. कहाँ पर है first और second reaction में?
Second.
Second reaction में. ठीक है. But is it on the left? Is it on the right hand side? The answer is no. ठीक है.
Left hand
तो
side.
मुझे क्या करना पड़ेगा? इसको फ्लिप करना पड़ेगा.
Yes. sir.
यानी कि माइनस टाइम्स करना पड़ेगा इसको. ऑल्सो आई वॉन्ट द कोफिशिएंट ऑफ C to be 1. यहाँ पर तो 2 है, तो मुझे क्या
रूट
करना
लेना
पड़ेगा?
Divide by.
डिवाइड
Divide
बाय
by
2
two.
करना पड़ेगा, है ना? तो
Yes.
दिस इज
Yes, sir.
as good as writing 1 plus minus 1 by 2 times the second equation,
Yes, sir.
Yes, sir.
है ना? तो अब k के साथ में क्या होता है? When I multiply the equation by something, तो k की पावर में चला जाता है वो.
Yes, sir.
तो ये k2 की पावर -1 by 2 हो जाएगा और ये k1 एज इट इज रहेगा और इक्वेशंस को ऐड करते हैं तो k मल्टीप्लाई हो जाते हैं,
K1 by root K.
राइट? तो योर आंसर विल बी k3 विल बी इक्वल टू k1 by root
K2.
ठीक है.
Yes, sir.
Yes, sir.
Yes, sir.
चलो एक और क्वेश्चन ट्राई कर लो. ट्राई वन मोर क्वेश्चन, ऑल्दो एक मिनट दो, लेट मी रब द आंसर. ठीक है, इसको ट्राई करो. हाँ, क्या आ रहा है? बी ऑप्शन.
B option.
करेक्ट. तो यहाँ पर लाइक यू कैन सी द थर्ड रिएक्शन is actually the first reaction
Minus 6.
Minus second.
minus second reaction, right? So K3 will be K1 upon K2 and that gives you B option as the answer. ठीक है.
Yes, sir.
Yes, sir.
चलो cool. All right. तो आज के लिए इतना काफी है. इसके आगे का हम लोग नेक्स्ट क्लास में कंटिन्यू करते हैं.
Yes, sir.
वैसे भी लोग कम होने लग गए हैं क्लास में, तो एग्जॉस्शन
हाँ,
आ
सर.
गया है. ठीक है.
Yes, sir.
Yes.
ऑलराइट, थैंक यू गाइस, टेक केयर, बाय बाय.
सर आप वो स्टोइचियोमेट्री के एग्जांपल्स दिखा सकते हो, वो रह गया था मेरा.
हाँ हाँ हाँ, बता देता हूँ. कौन सा वाला?
हाँ सर.
ये वाले?
हाँ सर, थोड़ा ऊपर बस. हाँ,
ये
yes, sir.
स्क्रीन.
सर थोड़ा नीचे जा सकते हैं. हाँ सर.